Okay, so we were to write find person binary search, and we wrote insertion sort last time that sorted them on age, correct? So I think we have that. So we added a bunch of persons to our people array. So we called our add person function. This guy up here. Well, this was add person from user, so if we wanted the user to manually put somebody in. But here's our add person function that took in a first name, a last name, and an age. It created a brand new dictionary, and then went ahead and inserted that dictionary into our list called people. Make sense? So we have a list of people dictionaries. All right, good. An array, what I've talked about from other languages, an array and a list are the same thing. Okay, so arrays are just collections of like things. Lists are collections of like things. All right, so in this particular case, we have a list that we've named people that is a collection. I thought Facebook wasn't supposed to show pop-ups while you're like screen capturing. That could be real dangerous. I have some, actually most of them are former students who are friends on there who might put some questionable content. Yeah, so an array is a collection of like elements. A list is a collection of like elements. We just happen to have created a variable named people that's holding a list, and the like elements that we're putting in there is a bunch of dictionaries. That make sense? Yep. So that in Java, we might create an array of dictionaries if you wanted to get the equivalent thing. So in Java, we don't have a thing. Actually, they do have a thing called a list, but what we're learning about lists are synonyms with, or synonymous with arrays in Java. All right. So this just creates a dictionary, then adds that dictionary to our list. Last time we wrote this insertion sort, which goes through and instead of comparing the dictionaries to each other for which dictionary is less than the other, it specifically looks at the age attribute of the dictionary and says, should this person's age come before this person's age? Make sense? All right. So that's the one new step we put into this, is we had to dig into the value at a particular bucket in our list, because it's not a simple value anymore. It's not just a number or a string. Now it's a dictionary that has stuff inside of that. Okay? And the next step we're going to be doing is looking at objects that have even more stuff inside of them, because they're going to have functions and things like that. All right. So we added a bunch of people to our people list. We printed out the unsorted list. We sorted it. Then we printed out the sorted list. So they should be in order of age. Let's just go ahead and test that real quick. It looks like I already had it. Oh, it's because of this guy here. So here, well, this was the last thing we ran at the end of class last time. So this is our sorted ages. So sorted ages should start here. So there's 18, 21, 23, 25. Seems to be ascending order. Okay. And remind me, so just for debugging practice, why do I have this error message right now? So indentation error, expected an indented block. If I go back to my code here, it's screaming about this guy right here. Why is that a problem? Yeah, so I have the start of a function here, right? So I got the little colon here, and whenever there's a colon, I actually think that's a pretty correct answer, is when you think about the interpreter, how the Python interpreter works. When it hits a colon, it's expecting one or more indented statements. So I think, I was going to say because all functions require a something after them, but I really think you hit the nail on the head with the exact colon aspect of this. So every colon expects one or more statements to appear after it. I have a couple of comments here, but these don't count, right? So it expects there to be at least one line. So if I just say print LOL in here, now the error is going to go away because I've included one statement in there. I'm never using age, but that's okay. Make sense? All right, so make sure you do look at your error messages so you kind of know what they're screaming about. Because that's a skill set in and of itself, debugging your code. And hopefully many of you are gaining practice. And that there should be two different levels of debugging proficiency that you're practicing during your homework assignments. One is the interpreter screaming at you, right? When you've written code that isn't syntactically accurate. And then there's the other one is when the interpreter says, hey, what you wrote is legal Python, but it's not doing what it's supposed to do. And sometimes those are the harder ones to debug, right? Because with the syntax there, it screams at you and gives you some sort of usually somewhat cryptic message as to what the problem is. But when it's a runtime error or a logic error, you got to go back and look at your own code and see, what did I write that didn't make a whole lot of sense? Make sense? Okay, so let's go ahead and write our find person binary search. So remember, this is our dictionary search or our phone book search, however you want to call it, binary search. It assumes our list is an ordered list, and we've already sorted it by age. So we have a bunch of, this guy's going to assume we're working with dictionaries. And it's going to be dictionaries where, at the very least, one of the attributes of each dictionary is age. Okay? Technically, it doesn't have to be a first name and last name along with it for this to work, but it has to have an age in there. Okay? So we're assuming it's sorted to begin with. The very first thing we're going to do, we're going to go to the middle. Okay? We're going to say, is this the guy we're looking for? That is this a dictionary that represents a person who has an age equal to age? If yes, go ahead and return. It should return the person. Return that dictionary. Otherwise, return -1. Okay? If not, should the age come to the left or to the right of this? Rinse, lather, repeat. Right? So we're going to need a couple of variables here. We're going to need to keep track of the beginning of our array, the beginning of our list. So the beginning initially is always going to be bucket 0. And the end is going to be the length of our list -1 for the last legal position. That's the range of values we're working with for the current portion of the dictionary we're currently focusing on, right? And then once I rip the dictionary in half and I only focus on one half of it, we'll shrink either end down or move begin up, something like that. All right, so we're going to go ahead and say begin is equal to 0. We'll say end is equal to, now we're not passing in our people list here. Instead, we made that a global variable. And I mentioned this last time. This is kind of in preparation for us segueing into writing our own objects. Because writing our own objects, we're going to have what are called fields. Variables that belong to the entire object. So we have access to all of those things within the different functions in our object. So this is kind of our little baby step in that direction. Okay, so we didn't have to pass that list in here because we already have access to it from up here. All right, so end will be equal to the length of people. All right. Then we need to go ahead and we need to calculate middle. And what's middle going to be? It's going to be end plus begin divided by 2. Okay, end plus begin divided by 2, so we have our middle.
Should you do double /2?
We should. Why? This is another example where I introduced a bug to test.
Otherwise, you're going to get like remainders in the bucket bins.
Yep. So a single slash gives us floating point division in Python. A double slash gives us integer division in Python. And actually, interestingly enough, in Java, we would have just used a single slash. If you have 2 integers you're doing division with in Java, it automatically does integer division. If at least one of those values is floating point, it does floating point division. Okay? Java does not have 2 different divide symbols. Okay? Java's divide symbols, it's one divide symbol, this guy right here, operates based on the type of the value to the left and the type of the value to the right. Because Java is a strongly typed language. Because it's a strongly typed language, every variable has a type associated with it. The type inference engine doesn't have to figure out what's in there. That makes sense? So we know about that ahead of time. So Java doesn't need two different operators for this. In Python, we're saying, look, we don't know at interpreter time what kind of value is going to come out of there. It could be an ice cream cone for all we know, right? You know, end and begin, they kind of sound like the beginning and end of something, but they don't have to be. We could put anything we want in there. It's a loosely typed language. Okay, in fact, they might not be the same thing each time through the loop. Right? We could change values left and right. So Python being loosely typed then has some consequences, right? We have the double divides and stuff like that. All right. So because we want to explicitly do integer division here, okay, it's either going to break the world. Okay, if this was an ice cream cone and we're trying to do integer division by 2, well, I don't know, you can split an ice cream cone into 2. I don't know what Python would do with that, but in real life, we can probably pull that off. But, you know, the idea is that we are explicitly saying, I want whatever this ends up being. I want us to do integer division divided by 2. Okay? Don't try to guess what I'm thinking. Just do what I'm saying to do. Make sense? So you're right. Double slash, you passed my test. I think I did not make the same mistake last time I wrote it. Pretty sure. Yeah. I write in a lot of different languages each day. Gonna give me a break. That's why I introduced the errors on purpose. I have a built-in excuse. All right. So middle is equal to end plus begin. Integer divide by 2. All right. Now we want to keep adjusting end and begin and calculating a new middle as long as we did not find the value that we were looking for, right? So while, well, a couple different things here, right? So as long as we want to keep going under 2 different circumstances, right? We want to keep going as long as begin is less than end, or less than, or actually we want to say, well, begin is not greater than end. So while begin is less than or equal to end, we're allowed to keep going, right? Then we would probably calculate our middle. Then we would ask the question, is the value at middle the guy we're looking for? If it is, return it. If it's not, update begin or end, loop back up, recalculate middle, over and over and over again. Okay, so we're going to hide that middle statement inside of a while loop. The while loop is going to be while begin is less than or equal to end. Okay, as long as that's true, that means we have a fighting chance at finding what we're looking for. So we'll go ahead and calculate the current version of middle. Then we're going to ask the question, is the value at middle? So if people at bucket middle. Now, what kind of animal is people at position middle? Cat, dog, string, or dictionary? Dictionary. It's a dictionary. So people at bucket middle is going to boil down to a dictionary. Okay. Specifically, it's going to be a dictionary that we've promised will have a field or have an attribute named age. So if that guy's age is equivalent to the age that we passed in, if I have found a person inside of my people list who has an age equal to the age I was searching for, then go ahead and, not this language. Then go ahead and return people at bucket middle. Make sense? Go ahead and return that dictionary. Otherwise, if we're still kicking right here, now we can write in else. We kind of talked about that before. You can view these ifs as kind of minefields. We know that return, what does return do again? You gave the same wrong answer last time. What does return do? Let's keep going. Doesn't have to do with loops. Yeah, ends the whole procedure. Yeah, ends the function. So return makes the function immediately end. So it doesn't matter whether you're in a loop, whether you're in an if statement, whether you're just standing out there on your own, it's over. This function ended. Okay, so the next, we would never, ever, ever get here. So this print statement is part of this if statement here, and I have it, and so is this return statement. So return and print are both members of this if statement. This is an unreachable line of code. You can never get there because the guy immediately before it that will always happen before we got to that guy is a return, which kills it off. Make sense? In fact, it'd be interesting here. I'm going to run this real quick. In a strongly typed language, it would give us a warning saying that this guy is a unreachable line of code. And since it appears to be doing it, it's a two-pass interpreter because it's yelling at us when we didn't have something following the colon here. I'm interested to know whether it tells us that's an unreachable line of code. Nope, it doesn't. Compilers would have. All right, so again, that's the difference between an interpreted language and a compiled language. Okay? So I would only be here if the if failed, right? Which means that I would only be there if I didn't return. Actually, this is the wrong way of saying this. I would only be here if the if failed and I did not return. Because the return is part of that if. If the if was true, we return a value, making the function immediately end. So if you view this as kind of like a minefield, we wouldn't still be kicking here unless we did not hit this return statement. So we don't have to write an else, but it's not incorrect to. In fact, when you do like maybe logic speak, it might sound better to write an else. If we found the value we're looking for, return it. Otherwise, let's do something else. What should we do? Well, we'll ask the question. If, and you can actually do an else if. There's a, I don't know if we've introduced this thing, the book probably did. There's an elif. So else if, we would ask the question like, if age is less than the value we're currently looking at, then we'd adjust one side. But if I'm just going to kind of say this all in, I want to break it into individual pieces. So instead of using an else if, I'm just going to say else. So if I didn't find the value I'm looking for, otherwise I want to do something else. What else am I going to do? I'm going to ask a new question. So instead of using elif, I'm going to say else, and then I'm going to write a brand new if. Equivalent, it'll be equivalent, okay? Else, if the age that I'm looking for should come before the age of the person we're currently looking at, then I want to update end to be middle minus 1. If it should come after, I want to then update begin to be middle plus 1. Make sense? So I'll ask the question here, if people at bucket middle, so and people is a list, so this is saying give me the index in that list of position middle, if that guy's age is less than the age that was passed in, that means that if the person I'm looking for exists, they're going to exist to the left of me. So I'll go ahead and update end to be equal to middle minus 1. Else, begin is equal to middle plus 1. That make sense? A lot of times, this syntax looks a little friendlier than that. Yeah, I mean, it's really the type of thing where the else if, so elif stands for else if, it just combines the two. Maybe reads a little funny when you look at it. So you pick your poison. They're logically identical, but typically when you kind of say things out loud, writing it like this more matches what you're kind of thinking. Do this, otherwise let's do other things. What other things? These things. I'll ask a new question. Okay? So we'll update, well, we've either died and returned the value we were looking for, or we've updated end or begin, okay? Which then allows us to loop back up, and we'll keep doing this as long as begin is less than or equal to end. Eventually, those guys are going to overlap each other, right? Which means we've checked everywhere. So we'll keep doing this, and if they eventually overlap each other, which means we've exited this while loop, then we'll go ahead and we'll return a -1. Make sense? All right. So that should be, just comment these out here real quick. Let's go ahead and print find person binary search, and let's look for age 18. So it should find this one at the very beginning, right? Okay, so it's going to give us the person who has age 18, which is Steve Jones. But we know that we're kind of testing our binary search algorithm to find it at bucket 0. So this will actually be when begin and end are the same over on that end. Okay, just because we know how binary search works. Making sure we don't, I'm kind of testing to make sure we don't miss the extremities. Because that's kind of a risk with binary search. Is sometimes you end up missing the very first or very last bucket because of a poorly written Boolean expression right here. Maybe you say it's less than instead of less than or equal to. Kind of a common mistake that you end up not looking everywhere. You look almost everywhere. All right, so we should find Steve Jones in this case. Row. List index out of range for people. So middle, it's saying, is out of range. N should be the last legal position in our array, not the length of it. Well, except it did not find our 18 there. So let's look at this guy. Begin less than or equal to end. It is. Let's go ahead and calculate middle. So how many things are in here? 1, 2, 3, 4, 5, 6. So bucket 5. So this should be 5 plus 0 divided by 2, which should give me a 2, okay, for our initial middle. Okay, so if people at bucket 2 get the attribute age, if that guy's age is I passed in an 18 here, right? That guy's age is an 18, go ahead and return that. It won't be, because we know that 18 is going to be at bucket 0. Okay, so should the age come before that? So if the person's age that I am, oh, I wrote this backwards. Of course. If the person's age is, if the age we're looking for is less than the age we're currently looking at, then update end. Okay, to move, so we're only focusing on the left half. So in this case, that's what we will do. So we're going to update n to be a 1. Okay, we'll loop back up. 1 plus 0 divided by 2 is 0. So middle will be 0. If people at bucket 0's age, which should be 18, is equal to 18, go ahead and return it. So let's make sure this works for this guy. So there's our Steve Jones, age 18. Okay. Now let's go on the other end of the spectrum. oldest person here is a 34. And we should do this correctly now. Our bug was, well, we had two bugs. This guy here, and then I was comparing the ages backwards. So we're going to look for 34 now, which should find the last guy, Clark Smith. So there's Clark Smith. Then we can find somebody in the middle. Let's look for a 25. So 25 should find Van. All right. Let's go ahead. I'm going to give myself 2 different 34s. Okay. Now, when we're searching for this, we're not necessarily sure which of these two we'll get. We could predict if we knew how our insertion sort worked and we knew how our binary search worked, right? We can decide which of these guys ends up being first when we sort them, okay? But in this case, we're not necessarily sure which of these two are going to end up being found here, but one of them will be, okay? This is where with a binary search, it's difficult to come up with the first occurrence of or the last occurrence of, because the way we're going about finding things is more of a divide and conquer type of approach. Okay. So we're actually searching for 34 now, not 25. All right, I think it's going to give me Clark Smith. Yeah, that was complete guess. It wasn't based on. All right, so and it should always give us Clark Smith, you know, given this order. All right, now if we happen to switch these two around. So the order we initially added them to the list, now it should give us Bill Smith, just because the order in which we bubbled stuff towards the beginning should set it up. That makes sense? So it had nothing to do with one being more important than the other. It was just the order in which they were originally added to our list dictated the order in which they presented after we sorted the list, which then drove the first one we bumped into when we were searching. Okay, so that is our find person binary search. Questions about that one? All right, so let me go ahead and I'll put this guy up on Slack. Okay. All right, so now that we've done the easy sort, I mean, insertion sort really was too easy, right? I mean, we need a more difficult sort than that. Well, I mean, we certainly don't want to go with the easiest sort of just calling the sort function that's built into Python. That's it. I'm completely cool with that. All right, so let's introduce a sort called merge sort. All right. Okay. Oh, merge sort's one of my favorite sorts. Reason I bring this up now is to introduce two new concepts. Well, first of all, to reinforce a concept we just learned, we learned this kind of divide and conquer concept with binary search. Okay, so divide and conquer is kind of a theme of algorithms in computer science. So there are many algorithms that exist in computer science that we characterize as being divide and conquer algorithms. It doesn't really mean much. That just happens to be the type of moves they make. They keep dividing data up to allow you to focus in on smaller pieces of stuff. like we just did with binary search. Make sense? So it doesn't really mean anything, incredibly technical. It's no more difficult than what I just said. All right. Now, before we can introduce merge sort, though, we have to talk about something called recursion. Anybody know what recursion is? Go ahead. Okay. It is doing something over and over again, but that could also be a loop. So how does recursion differ from that? Go ahead.
Recursion is when you recursively call a function.
What does recursively mean?
Recursively means doing something recursively.
You cheated on that one. All right, so recursion is a couple different ways we can say it. It's when a function is defined in terms of itself. Or maybe more bluntly put, when a function calls itself from within itself. Okay? That makes some sense? So, a good example of recursion for a real-life problem is factorial. So, the factorial problem. So, for instance, we've seen 4 factorial, right? 4 factorial is equal to 4 times 3 times 2 times 1. Okay, which is 4 times 3 is 12 times 2 is 24. That's 4 factorial. Now, isn't it true that 4 factorial is actually equal to 4 times 3 factorial? And 3 factorial is actually equal to 3 times 2 factorial. And 2 factorial is actually equal to 2 times 1 factorial. And 1 factorial is actually equal to 1. So let's go ahead and let's implement factorial both recursively, well, let's do it iteratively first, and then recursively. Okay, now, truth in advertising. Most of you are not going to like recursion initially. Now, it's actually not necessarily a bad thing. It's the problem with it is, well, I would say the problem with it. The difficulty with it is that we're already working on changing the way we think, right? Okay, we're already all struggling with, thinking about problems in terms of the little tiny baby steps that a computer needs to follow to solve those problems. Okay, now I'm asking you to take it to another level and say, okay, well, how can I have functions call upon themselves within themselves? Often this means instead of loops, do recursion. Okay. Now, one thing I will say though is recursion is not better than iteration, than loops. Okay. So I'm not introducing it as an upgrade. There is a point to it. Recursion typically leads to pretty elegantly written solutions, and we'll kind of see that with factorial. I'll write the iterative version of factorial kind of as long-winded as we can, not taking too many like shortcuts, so that you'll see that, and then we'll write the recursive version as short-winded as we can. You'll see that typically recursive solutions are substantially shorter than the iterative version of that solution. Okay? Now, so that's one possible benefit, although I've kind of advertised that the length of the solution doesn't necessarily matter. Okay? Now, recursion, so let's kind of get back here. Let's write some of these features here so we can say pros often, well, let's just do it all in the same line. Shorter and more, I don't know how to spell that word? Elegant solutions for whatever, if one solution can be more elegant than another solution. Okay, so often the solutions might even look cryptic because they're wrapped in terms of themselves, like we just looked at here. that 4 factorial is actually equal to 4 times 3 factorial. Oh yeah, that makes sense because 3 factorial is 3 times 2 times 1. Well, 3 factorial is actually 3 times 2 factorial. Oh yeah, 2 factorial is 2 times 1. So there's elegance to that. We've noticed kind of a truth about something, and rather than writing extra code, we've gone ahead and said, well, how do I calculate 3 factorial? I call my same factorial function and say, calculate factorial of this guy. Well, how do I calculate 2 factorial? I call the same function again and say, calculate this guy. All right, so we often have shorter and more elegant solutions. Cons. We might say they're a little bit more difficult to understand. I'm not sure that's fair to say because I think that has more to do with experience. Okay, but these guys are definitely memory inefficient. If I'm calculating 4 factorial and I have to pause that version of that function to wait for the answer to 3 factorial, that means I have to put all of the current variables associated with my call for 4 factorial on hold. So I can make a brand new call to that function passing it a 3 for 3 factorial, which I then need to put that guy on hold. So I can make a brand new call for 2 factorial. I then need to put that guy on hold so I can make a brand new call for 1 factorial. And then finally I can just return 1. So I actually have 4 copies. For 4 factorial, I have 4 whole copies of this function sitting on what's called the stack. Okay, operating systems have this thing called the stack. Okay, sitting on the stack in order to, actually it's the stack related to the programming language, which we'll talk about in 470, in order to actually implement recursion. That seems invasive, right? It's a lot of extra memory we're taking for solving what really is a pretty simple problem. So realistically, we choose factorial as our introduction to recursion because it's a simple introduction. But if you were writing factorial, it would not be wise to write it recursively from a memory perspective. It's a pretty easy problem to write iteratively. It's kind of roll with that, I guess. All right, so they are memory inefficient, so we want to use them sparingly. Now, another thing is some problems are only solvable recursively. Okay? Every now and then you'll run into a problem. Well, actually, that's not fair to say. Some problems are only conveniently solved recursively. Now, we could make a comment like this. So this is more of a note. Okay? Any problem that can be solved recursively can also be solved with a loop and a stack data structure. Now the problem here is we don't know about stack data structures yet. So since we can't write a stack data structure yet, we're going to kind of be stuck with recursion for problems that lend themselves to recursion. The good news for us, since I'm telling you right now you won't like recursion at first, I say at first because what will end up happening is in a couple of years when you all take 470 with me, which is the programming language theory class, we implement a programming language in there and we'll write recursion. We'll implement recursion. And I use a language in that class called scheme. Okay? And that is a functional language. Remember when we were introducing the different types of languages and I kind of just glazed over functional languages? I said, don't worry about this right now. Okay, scheme doesn't have loops. So whenever you need a loop, you're going to be writing a recursive call. So you end up coming out of that class thinking very recursively. And it's hard to get back into the iterative mindset. Okay? But what will end up happening as an accident is you will end up being comfortable with both iterative and recursive solutions then. But for right now, I promise you're not going to really like recursion. So just kind of prepare your soul, for that. Okay, you'll actually be okay with factorial, but I won't actually give that to you for homework assignment. Your first recursive homework assignment will be merge sort, which you were just going to absolutely hate. Oh, it's a nightmare. It is a nightmare. I can't solve it. Well, not without bugs, at the very least. All right, so let's go ahead and write these couple things real quick in our last few minutes just to introduce recursion. All right, I'm going to go fairly quickly since we're a little stuck on time here. So I'm going to say dev fact iter. So this will be the iterative version of factorial. And this guy is going to take in a num. And what we're going to do is we're going to build up our answer as we whittle num down to 1. So we'll say answer is going to start off as 1. Then we're going to say for num in range of num, comma, 1 step by -1. So we'll go 4, 3, 2. We don't actually have to go to 1 because 1 times anything is the anything. Okay? And we'll say answer is equal to answer times num. And actually, instead of using num here, I'm going to actually say I. And we'll say I here. So we'll define I in terms of num. So I will start off at, if we passed in 4, I will be 4, then 3, then 2, then that's it. It won't hit 1 because we didn't include 1 here. All right, and then ultimately, after that for loop is done, we'll return answer. All right, so that's the iterative version of factorial. Recursive version of factorial is if num is equal to 1, return num. Return num times fact minus 1. So that's the recursive version of factorial. If the number that was passed in here is equal to 1, go ahead and just return it. Return 1. Otherwise, return the current value of num times whatever fact recursively returns for num minus 1. So we have to wait for this result to come through. All right, let's just see this real quick. Print fact iter. We'll pass it a 4. Print fact recurse. We'll pass that a 4. And we get 24 out of both of those. Both of them ultimately came to the same answer. All right. Now, I'm going to give you a reading assignment over the weekend, not a programming assignment, because believe me, it would not be fair for me to tell you to go read about merge sort and write it. Okay? That would not translate well into faculty evaluations. So, and a couple of you in here have had classes with merge sort, and you can all attest to that.
That's why it would have been easy.
Well, you would have had to write in Python. All right, so let me just go here. Is this, that's not us. So I want us to start reading about objects. Let's read 9.1 through 9.5 over the weekend, do all the little exercises. And then what we'll end up doing is maybe we'll end up writing merge sort in terms of object or something like that. But, you know, so I'll introduce merge sort on Monday. Okay, so read 9.1 through 9.5. But
Do you have all chapter 8 read?
all of chapter 8 read.
Is it just a dictionary?
I would say probably, but a lot of it's not going to be really life-changing. So, I mean, this last part, dictionary nesting, is having a dictionary which contains an attribute that is also a dictionary. So, finish reading chapter 8, I think, would be fair, but definitely read 9.1 through 9.5. If you have not already done so, make sure you contact Professor Josh Locklear at joshua.locklear@cu.edu if you want to do the hackathon next Saturday, and if you want to do the hackathon boot camp thing on Tuesday night with me. Highly, 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 highly encourage all of you to take advantage of that. You'll learn a lot. All right?